Hello, everyone, and thanks to the organizers for putting together this online workshop on ultra-high frequency gravitational waves. My talk is about gravitational wave spectra and their features from preheating after inflation, where oscillons are formed. So let's take a look at the data we have and the preferences those data have, in a sense, for inflationary models. These are the latest results from the Planck satellite mission. And we can see that there's a definite upper bound for the tensor scalar ratio, right, at the level of r equals 0.07 and below. This means that convex potentials are essentially ruled out. So inflation, the data from the CMB tend to push inflation towards potentials that are shallower than quadratic at large distances, so during inflation. And this means that highly likely we need to consider models with plateau potentials. So during inflation, we know what a shallow potential does. We have this inflaton field sort of denoted by these red dots. And during inflation, we are slowly rolling along this potential. And this is where the CMB modes exit the horizon, and that's how we get all the information about inflation. So assuming that we have just a single scalar field, so we take a very vanilla model of inflation, a single scalar field rolling in a potential, having a minimum at some point, right? So after inflation ends, the field oscillates around its minimum, and we will also assume that around this minimum, the inflaton potential can be described as a massive scalar field, so it has a quadratic term plus higher order terms. So during this phase where the inflaton oscillates around its minimum, it has to transfer its energy into other degrees of freedom, because we know the universe has to be in a radiation-dominated state by BBN. So somehow the energy must be transferred from the inflaton to other fields. So simple interactions one can write down involve just decays of the inflaton to either bosons or fermions. Now, in the case that the inflaton talks to some boson field, then something called Bose enhancement can take place, which just broadly means that if a certain mode of this daughter field is populated, then there's a higher chance that more particles with this wave number will be produced. So mathematically speaking, it's very simple to write down the Klein-Gordon equation for this daughter field chi, and we see that it has an effective mass which depends on the inflaton field. Now let's forget about the evolution of the universe, or the expansion of the universe during reheating for a moment, and take the inflaton to be just a sinusoidal function. Then we get the Matthew equation. So we know that a differential equation of this form, which has periodic coefficients, can be solved in a very sort of simple way. The solutions are just products of periodic functions with the period of the original time dependence of the parameters, times an exponential of mu t, where mu is the Floquet exponent. So the Floquet exponent can be real, imaginary, or complex. If it's imaginary, nothing important happens in a sense. The solution will be just a periodic function with some shifted frequency. But if it has a real part, so it's either real or complex, then we see that certain solutions, right, grow exponentially. So this can be visualized using a Floquet chart, and we can see that depending on where you are on this chart, so what for a given phi naught, so for a given inflaton amplitude, depending on the wave number, right, of each mode, it can either be exponentially amplified if it's in one of these instability bands or not. And we can see it here like clearly in an example. Now, in real life, the universe is expanding, which means the physical wave number of any mode it will redshift. So as it redshifts, it will cross perhaps several instability bands. Right? So the intuition of exponential amplification still remains, but the details, like the quantitative details, are a bit more difficult because, for example, this mode will be amplified here, then not amplified, amplified again, and so on. So we see that in an expanding universe, we again see particle production for specific wave numbers, but it's a bit more erratic than in the very clean-cut case. of a static universe. Now, in order for this phenomenology to happen, we don't necessarily need a second field, right? All we need is a scalar field, the inflaton, with a self-interaction. So a field with a self-interaction can again lead to parametric enhancement of certain wave numbers, right? So certain wave numbers of the inflaton get amplified, right? As they get exponentially amplified, at some point, the amplitude of certain wave numbers becomes large enough that the linearized equations of motion stop being valid, right? So we start probing nonlinearities of the potential. And this is now the important part. So we know that once you start probing nonlinearities from optics to field theory, right, interesting structures can emerge. In optics, we can have the so-called self-focusing media. So we can have media where the refractive index is a function of the intensity of a beam propagating through that medium. And this can lead to self-focusing, right? This can lead to essentially the refractive index being bigger when the intensity of light is larger. And this will, any beam will tend to self-focus. Now, there are two forces at play here, right? There's the self-focusing of this medium, and then there's the diffraction. If those two can balance each other out, we can get a light pulse that propagates without distortion. Now, in field theory, the self-focusing of the medium is played by the potential. So as long as the potential for some value of field amplitude is shallower than quadratic, so v prime of phi is smaller than m squared phi for some field range, then this is effectively an attractive nonlinearity, right? So if the field has an attractive nonlinearity, once the amplitude of the field or the intensity or the number of particles gets large enough, we can see this sort of self-focusing idea again, leading to Oscillon formation. Now, we have many studies have seen this numerically. So at the end of inflation, after this plateau potential, the inflaton oscillates, it generates fluctuations, right? Those fluctuations at some point become large enough that they probe the nonlinear part of the potential, and then these structures emerge where dispersion is actually counterbalanced by this attractive nonlinearity. Now, an interesting thing about Oscillon formation after inflation is that they generate gravitational waves. So during this turbulent regime, right, of the homogeneous inflaton being fragmented into generating fluctuations, and other fluctuations becoming large enough that the whole inflaton is fragmented into these blobs of matter that you see here, a large amount of gravitational waves can be emitted. And two different sort of features have been seen in the literature, right? The gravitational wave spectrum can either have features, and those features, right? So one peak, one sort of valley, and another peak. So these are related to the frequency content of the oscillon itself, right? So essentially, the position of these peaks tell us about the frequency content of the oscillon, or they can be sort of more broad thermal-looking spectra for the gravitational waves. Now, the question that arises is how are the shapes of gravitational waves related to the potential of the inflatons, or what can they teach us if we were to observe them? So we did sort of two experiments along these lines. In one sort of type of experiment, a numerical experiment, we took an axion potential, right? So a potential that is linear at large distances and quadratic at small distances. And what we did was we altered the small field behavior of this potential by approximating it using the Padé approximation, right? By this x squared over 1 plus x squared, we see that this is linear at large distances. And we had some ratio of polynomials, right? And the larger the degree of the polynomials was, the closer we were to this full square root potential. And here you can see the blue is the sort of perfect axion monodrome potential, and the different colors are approximations of different orders. Now, the second family of models we looked at was we took a simple plateau potential, Again, at large distances, this goes to 1, right? This goes to a plateau. Whereas at small distances, at small field values, this is quadratic. And we can change, so this is this black potential here. So we can change the slope of the potential at large distances, right? By changing this parameter alpha 1. We can change the height of the plateau by introducing this parameter alpha 2, or we can change the transitional period between the quadratic potential and the plateau by this parameter alpha 3 here. So there are 3 different deformations of the same potential. So now the question arises, we have this essentially one family with 3 parameters and another family with 1 parameter, being this polynomial degree. How does playing with these parameters change Oscillon formation and gravitational wave emission? So here I just show you the 2 different families, the axial monodromy and the plateau potential. And for the plateau potential, I only take one of the 3 realizations, right? I only take sort of this alpha 1 deformation. Okay, so there are a few things we see. First of all, let's look at the gravitational wave spectra. We see quite different features, right? So for this plateau potential, we see a very smooth spectrum. For the axial monodromy, we see this double bump potential. By the way, the axial monodromy was also the model used in this paper that actually discovered this double peak structure. Furthermore, if we look at the axial monodromy potential on its own, we see that the order of the approximation that we use doesn't really affect the features of the gravitational wave spectrum. It does affect Oscillon formation. So the red one is the least approximated potential, so the one that deviates more from the perfect square root. So for the others, we see that they reach a plateau, right? The number density of oscillons does not strongly depend on the approximation. Something that does depend on the approximation very strongly, though, is when oscillons start being formed, right? So we see that the red curve, which is later, exhibits later oscillon formation, and this is the least approximated potential. Okay, now, so the important thing that we need to somehow address is the fact that in one family we get features, in one family we don't. Now, let's look at the time evolution of this gravitational power spectrum. So we go again to the sort of alpha 1 deformed potential, so the potential that is a plateau, but can be also linear at large distances if alpha 1 is 1. Initially, the gravitational wave power spectrum exhibits a single peak. So if we think about what happens, initially linear fluctuations grow, right? Those linear fluctuations can seed gravitational waves. Then oscillons get formed, right? And then oscillons sort of stay there and the rest of the fluctuation redshifts away. So initially we are in the linear or quasi-linear regime, and we don't see much difference, right, between the 3 parameters for the plateau potential. Now in the second panel, after some time has elapsed, oscillons have clearly formed, and we see that because we see this 2-hump structure, right? Again, in pretty much all of the cases, all of the parameters. Now, as time progresses, we see that somehow this 2-hump structure starts being washed out, and at the end of the simulation, it's completely gone. Right? So it would be a bit oversimplifying to say that one family has features, the other one does not. In truth, both families have gravitational wave spectra with features, but in one of them they remain, in the other one they get washed away. Now let's look also at the scalar power spectrum. The scalar power spectrum follows somewhat similarly what we see in the gravitational waves in the following sense. Initially, the linear fluctuations govern the evolution. So let's look at this plateau potential here. right, initially we see a very kind of standard instability band, right? And at some point here we see the deviations from linearity. So we start probing nonlinearities and forming oscillons, and at late times we see some sort of thermal looking spectrum. Here we capture, or we compute the oscillon formation. So the oscillon characteristics, their size, meaning their width in physical, like in X space, and rho core, so the amplitude or the energy density of the field at their maximum, for the axial monodromy potential and the plateau potential. So we see that the oscillon formation, sort of the shape size relation, is very clean in the case of axial monodromy, and it's somehow dirtier or a bit messier for the case of plateau potentials. And here we did not make that much of an effort to look at true oscillons. We looked at just big enough overdensities. So here we get a mixture of true oscillons and sort of overdensities. And we can see that there's a mixture of those because if we check which of those overdensities stay where they are and which of those overdensities are gone after some time, right, either move or disappear, then we get the green dots. So the green dots are the sort of oscillons that disappear. So we see that a bunch of what we would call oscillons, right, so localized objects, are not very stable. So they are transient overdensities in the language of the literature. Now let's look at the Floquet charts. So the Floquet chart for the axial monodromy potential gives us Floquet exponents of 0.04, 0.05. The Floquet chart for the plateau potential gives us roughly triple this magnitude. And we can also see here exactly what we saw before, that initially, so the solid lines are the numerical data and the dashed lines are the analytics. Initially, the analytics and the data match very well, and at some point you start probing nonlinearities and there's interactions, nonlinear interactions between the modes. But we also see that the scalar power spectrum in the case of axial monodromy grows much weaker than in the case of plateau potentials. Now, at the end of the day, we can also check the effective mass of the two models, and the effective mass of the plateau potential has a large or significant negative part, right? Because plateau potentials actually have a V prime prime that's negative, so they exhibit tachyonic resonance, whereas axial monodromy potentials exhibit sort of traditional parametric resonance. So it seems like potentials exhibiting efficient self-resonance tend to give featureless gravitational wave spectra, right, and an earlier formation time. So at the end of the day, the result is quite simple. When you get strong resonance, right, then a lot of wave numbers are amplified. Some of them will tend to give oscillon, right? Some of them will have the correct shape characteristics that will be captured by the oscillon attractor. But there's also another large amount of fluctuations in our box, which are still gravitating fluctuations, right? There are still overdensities that move around the box, but they're not oscillons. These are these green fluctuations here. And they still continue to gravitate after oscillons have formed, right? And these are the ones, their gravitation, that smoothens out the gravitational wave power spectrum after oscillon formation, giving them this sort of thermal looking shape. So the featureless shape. Whereas potentials with weaker self-resonance, right, give a gravitational wave spectrum that still keeps its peaks and valleys. And the reason for that is that parametric resonance is not strong enough to produce all this sort of abundance of random overdensities in our box. So fewer modes are amplified, right? Those that do get enough amplified will form oscillons, right? But after oscillons are formed, there's no other random noise in the box with sufficient power to produce a sort of overwhelming thermal looking gravitational wave spectrum. So in essence, by capturing the shape of gravitational waves from preheating and decoding the characteristics, we will be able to say whether or not there was efficient preheating leading to some smooth gravitational wave spectrum, or if there was some weaker parametric style resonance that gave an oscillon dominated phase without any sort of additional large fluctuations. Okay, so I think I'm a bit over time, but thank you very much and looking forward to the discussion session.